Okay, so we're going to talk about a concept that's related to limits called continuity. And you're kind of familiar with this already. We're just going to formalize what it means. So we're going to look at this graph, this function f of x. We're going to fill out this table for the graph. So in the first column, we're going to say if the function is defined at these x values. And if so, what's the value? So if we start at -6, at -6, it's not defined because at -6, there is no closed dot. So it's not defined at -6. At -3, it is defined. There is a closed dot at -3 too. So it is defined at -3 and the value is 2. At 0, it is defined. There is a closed dot at 0. The value is -1. At 2, it's not defined. There's an asymptote at 2. At 6, it's defined. There is a closed dot, and the value of the closed dot is 1. And at 8, it's defined. There's a closed dot at 8. The value is -4. All right. All right, so now we're going to talk about the limits at each of those places. So if I look at the limits at each of these values. So we'll start with the limits from the left, right? From the left, the limit at -6 would be 5, right? And from the right, the limit at -6 would also be 5, which means that the limit at -6 is 5. But this function is not continuous at -6 because there's a hole there. Continuous informally means that you can draw the graph there without picking up your pencil to make a hole or a break or an asymptote. So the function's not continuous at -6 because we have to pick up our pencil to draw the hole that's at -6. Okay, so then -3. From the left, the limit would be 2. Right, the limit would be 2. From the right, the limit would be -4. And because those don't match, that means that the general limit doesn't exist. And the function's not continuous there. We have to pick up our pencil to draw the break that's there. All right, at 0. At 0, the limit from the left is -1. From the right, it's -1. Those match, so the general limit's -1. And the function is continuous there. I can draw this portion of the graph through 0 without having to pick up my pencil to draw a break or a hole or an asymptote. So at this spot, the function is continuous. So we're going to look at how that's different from the other spots that we're talking about. Okay, at 2, the limit from the left is infinity. It goes up at the asymptote from the left. From the right, -infinity. Those don't match. And it's not continuous there. We have to pick up our pencil to draw the asymptote. All right, at 6, from the left, it's 4. From the right, it's -2. Those don't match. And we have to pick up our pencil to draw the break. So not continuous there. And then the last one, 8 from the left, -2. From the right, -2. Those match, so the limit's -2. But it's not continuous because there's a hole there. We have to pick up our pencil to draw the hole. So you'll notice the only place where the function was continuous was at 0. And notice the values here. The value of the function and the value of all the limits were the same. And that's the only place where that happened, right? So that's leading us to a more formal definition of what it means to be continuous. There are 3 requirements for a function to be continuous. So we're going to talk about what those are now. So if you look back up here at the top, we're going to fill in the 3 requirements for continuity. In order for a function to be continuous, whoops, hold on, that's not what I want. In order for a function to be continuous at A, f of A has to exist. That means that there has to be a closed dot. Right? F of A has to exist. The limit as x approaches A, oh wait, I'm sorry. I said that the wrong way. It's not really that big of a deal, but f of a, has to be defined. And the limit as x approaches a has to exist. So that means that there can't be breaks or asymptotes. And then the last requirement is that those two things have to be equal. That the limit as x approaches a and f of a have to be equal to each other. That means that there can't be any holes. Right? So there has to be a closed dot. There can't be a break or an asymptote. There can't be a hole. So these are the three requirements. So we're going to look at some examples in this other graph that's on your paper and tell whether or not the function is continuous at those places. So let's look at the other graph on here. All right, so we have the graph of the function g of x pictured to the right, or in this case to the left, has several x values for which the function is not continuous. For each of the following, use the three-part definition of continuity to determine if the function is continuous or not. So if we look at -8, well, that's so hard to read. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. At -8, I believe that's right here. This function is not continuous because the limit as you approach -8 doesn't equal f of -8. There's a hole. And so the limit is at the hole, but f of -8 is at the closed dot, and those two things don't match. The function is defined there. There is a closed dot. The limit does exist there. So it meets both of the first two requirements, that the function be defined and the limit exists. But it fails on the third one because those two things aren't equal. There's a hole. The limit doesn't equal the function value. The closed dot isn't where the limit is. Right? At -6, it is continuous. The function's defined there. There is a closed dot there. There is a limit there. And those two things are the same. So it is continuous. I don't know why I put const. Continuous. And then at -4, it's not continuous. You know which rule it breaks, 1, 2, or 3? Let's see, it doesn't break rule 1 because the function is defined there. There is a closed dot, but it does break rule number 2. The limit as x approaches -4 for this function doesn't exist because the two halves don't meet up. Okay. So we're going to talk some more about this definition of continuity tomorrow, but the big thing is to know the three requirements for continuity, both in math terms and then also in what do they actually mean terms.